All right, guys, so today we are going to be starting our investigation of the unit circle and how we're using some of the special right triangle relationships that we've talked about and relating them to some similar right triangles in this unit circle. So this page isn't in your notes. You can get started and flip to page 9. But this is something I just wanted to introduce what the heck the unit circle is. This goes along the lines of what we talked about last class. Sometimes we just do trigonometry. We don't really understand why or what we're doing. And I know you did some study of the unit circle last year, but you may not have really dug into what the heck it is, or you may not remember. So that's what this lesson is for. So what I have in front of me is the unit circle. So all it is, I know we are used to looking at it like it looks like on page 9 of your notes, where it's a kind of a very big zoomed in version, but this is the unit circle. It's a circle with a center at the origin with a radius of 1. So you can see I drew my little tiny radius of 1 here. So I drew a little tiny triangle. There's my radius. And I just kind of pretended this was a 30-degree angle. So this 30-degree angle, that's one of our 30, 60, 90 special right triangles. So I know my opposite side is 1/2. And my adjacent side here would be that radical 3/2 relationship. So that's some of the stuff we practiced last class or 2 classes ago. So what this unit circle does is it allows us to kind of boil down just to a really basic, easy to use triangle that always has this nice hypotenuse of 1. And the reason we're able to do this and we can apply it to a lot of other shapes is because they're always similar. So if you think back to geometry, if I wanted to dilate this unit circle, this triangle, if I wanted to dilate this triangle by a scale factor of 6, I could do it just like that. So everything is 6 times bigger. So the hypotenuse is now 6. The opposite side is now 3. The adjacent side is now 3 radical 3. Everything got 6 times bigger. But if I wanted to actually find the ratio of the sides, the opposite divided by the hypotenuse is the same ratio. All right, the adjacent divided by the hypotenuse is still radical 3/2, which is the same thing as 3 radical 3 over 6. So even though the triangle is 6 times bigger, the relationship of the sides is still the same. So we use this knowledge of similarity. We use this knowledge of dilations to allow us to relate any triangle, no matter whether it has a radius of 6, a radius of 1, to use sine, cosine, and tangent, because the relationship of the sides are all the same. So I hope that makes sense. So let's do a little diagram. So this is what I want you to start on page 9 of your notes. There's our definition of the unit circle. And we're really just going to fill in a bunch of ordered pairs on this circle. All right, so we have our unit circle. There's your definition. Pause if you need to. Little side note here. We're going to dig into that a lot more in the future, but keep in mind, well, we'll come to that in a second. But on this unit circle, these are some points that we can label really clearly and accurately. So if this is the point 0, 0, all right, you don't really have to write that, but just a reminder, that's all that is the origin. This point would be 1, 0, right? Basically just an XY pair. This point would be 0, 1. This point would be -1, 0. And this point would be 0, -1. So just thinking about these as ordered pairs. They're all just X, Y ordered pairs. I can mark in the degrees here. If we're thinking about angles as rotations, like we talked about last class, this is my starting side right here. That's like my initial angle. So we know this could be 0 degrees or 0 radians. And if we do a full circle, we can also think of this point as 360 degrees or 2 pi radians. 90 degrees, pi/2 radians. 180 degrees, pi radians. That's one of our very common, that's how we use our conversions, that 180 and pi combination. 3/4 of the way around the circle is 270 degrees or 3 pi/2 radians. And then we mentioned all the way around is 360 degrees, or 2 pi. Okay. That's the easy part. So really just thinking about everything on this page as a set of ordered pairs. So what I'm going to do now is I'm just going to draw an arbitrary angle here in quadrant 1. So thinking of this as an angle of rotation, it's always the angle away from the x-axis. We'll just call that theta. So if I turn this into a right triangle, we can kind of glean a lot of information about this ordered pair. So this point on the unit circle, if you kind of think of it like a string, if the point is here and it's going up around, just think about this as connecting it to the origin and just like wrapping all the way around and making connecting this to our unit circle. If I were to count over and up here, if I just wanted to think, okay, what is that point? This is the over and this is the up. So this ordered pair is just the xy, okay? Or just the xy distance that I went over and up. We can also mark in this hypotenuse as 1 because we're on the unit circle. So that's where we used our Pythagorean theorem down here. A squared plus b squared equals c squared. So x squared plus y squared equals 1. So we can have a triangle kind of over here in quadrant 1. So now what is really what's really cool about this and how we use this to our advantage. If I were to ask you guys, okay, what's the cosine of angle theta? What's the cosine of theta? Cosine is the adjacent over the hypotenuse. So the cosine of theta is the same thing as the x coordinate. So instead of writing this as an xy pair, I can think about this in terms of cosine. So cosine theta is my x coordinate right there. We can do the same thing for the sine of theta. Sine of theta equals the adjacent over the hypotenuse. And that should be y. All right, so it's a really, really useful piece of information. I can now think of these as interchangeable. I can use the y value and I can represent that as the sine of my angle. And I can think about the cosine or the x value as the cosine of my angle. And then we can even go a little further and bring tangent into it. Tangent is opposite over adjacent, so really not much to do here. Tangent of theta equals y over x. So there's our unit circle. So we can also bring this and we can write another angle. And I'll actually kind of think about some geometry here. I'll use a vertical angle here. So this is kind of a same angle theta. Let's build ourselves another right triangle. So I want you to pause the video for a second and think about what might change here. Think about what the ordered pair might be here and see if you can label that ordered pair. So I'll give you a second to kind of do a little brainstorming and then I'll label it for you in a minute. Okay, so since we are now in quadrant 3, this ordered pair, it's still an xy ordered pair, but since we're in quadrant 3, we have to go left and down instead of right and up, so these ordered pairs are going to be negative. Kind of an important observation. The hypotenuse is its own thing. The hypotenuse is just the distance really from the center to the point on the circle. So that hypotenuse is never going to be negative. The x and the y coordinates, that's where we'll have some negative values. But we can do the same thing. So the cosine of theta adjacent over hypotenuse is negative x in this case. So we can think about this as negative cosine theta. The x coordinate is negative cosine theta, and the sine coordinate is negative sine theta. So that angle can tell us kind of what the x and y values are at this point on our unit circle. So it's a really big idea, but really a main thing that I want you to take away from this, and we're going to write this again down at the bottom, but cosine of theta is related to the x coordinate, sine of theta is related to the y coordinate on this unit circle, and the tangent is the y divided by the x. All right, and we're going to go next class. We're going to fill this kind of bigger table in next time, so don't worry about that. But let's kind of put it all together. So you can see my triangles. These two diagrams go with this chart here. So I'm going to make that. That looks great. So the trig function for a point not on the unit circle versus a point on the unit circle. So the only difference here is kind of like what I showed you on our little introduction here, is if we have a dilation, if we have dilated our hypotenuse, okay? So instead of using a 6 like I did there, I just called this hypotenuse like an arbitrary, I just called it r for radius. All right, because that's really what it is now. If we're thinking about this as a point on the unit circle, yeah, it's the hypotenuse, but what it really is the radius of our circle, however big the circle is. So for a point not on the unit circle, the sine ratio is opposite over hypotenuse, so y over r. The cosine ratio is the adjacent over the hypotenuse, and the tangent we can still think of as opposite over adjacent. So it kind of takes the hypotenuse, that r value doesn't really affect the tangent. And then the same thing, this is what we just looked at above, for a point on the unit circle, the sine value is just y, the cosine value is just equivalent to the x coordinate, and the tangent is y over x. So keep this in mind for next class. We're going to use our 30, 60, 90s, and 45, 45, 90 triangles and relate it to this unit circle. Then we're going to start looking at some exact values using reference angles. So please, please, please let me know if you have questions. I will see you guys next time. Have a good night. Bye.